Dear students, welcome to Ali Bros EduSoft YouTube channel. I am Anjana Krishnan and I am here with you to discuss about the first chapter in mathematics of class 10 under Ncert syllabus. The first chapter is real numbers. Today we start with the session 1.3, the fundamental theorem of arithmetic, because the other portions are deleted for this current academic year. So our first session, the fundamental theorem of arithmetic. Every composite number can be expressed as a product of primes, and this decomposition is unique apart from the order in which prime factors occur. The fundamental theorem of arithmetic. Every composite number can be expressed as a product of primes, and this decomposition is unique apart from the order in which prime factors occurs. For example, 6 equals 2 into 3, 231 equals 3 into 7 into 11. Next example. Find the HCF of 96,404 by the prime factorization method, hence find their LCM. Question. Find the HCF of 96 and 404 by the prime factorization method, hence find their LCM. The prime factorization of 96 and 404 gives 96 equals 2 raised to 5 into 3, 404 equals 2 raised to 2 into 101. Therefore, the HCF of these two integers is 2 square equals 4. Also, LCM of 96 404 equals 96 into 404 divided by HCF of 96 404 equals 96 into 404 divided by 4 equals 9696. Move on to the next question. Check whether 6 raised to n can end with the digit 0 for any natural number n. Question. Check whether 6 raised to n can end with the digit 0 for any natural number n. Here, n is a natural number and let 6 raised to n end in 0. Therefore, 6 raised to n is divisible by 5. But the prime factors of 6 are 2 and 3. Implies 6 raised to n equals 2 into 3 the whole raised to n. That is, in the prime factorization of 6 raised to n, there is no factor 5. Since by the fundamental theorem of arithmetic, every composite number can be expressed as a product of primes, and this factorization is unique apart from the order in which the primes factorization occurs. Therefore, our assumption that 6 raised to n ends in 0 is wrong. Thus, there does not exist any natural number n for which 6 raised to n ends with 0. Next, revisiting irrational numbers. A number is said to be an irrational number if it cannot be expressed in the form p by q, where p and q are integers and q not equal to 0. A number is said to be an irrational number if it cannot be expressed in the form p by q, where p and q are integers and q not equal to 0. For example, root 2, root 3, root 5, minus root 2 by root 3, pi, etc. Next theorem. Let p be a prime number if p divides a square, then p divides a, where a is a positive integer. Theorem. Let p be a prime number if p divides a square, then p divides a, where a is a positive integer. Proof. Let the prime factorization of a be as follows. A equals p1, p2, etc. pn, where p1, p2, etc. pn are primes, not necessarily distinct. Therefore, a square equals p1, p2, etc. pn into p1, p2, etc. pn, that equals p1 square, p2 square, etc. pn square. Now, we are given that p divides a square. Therefore, from the fundamental theorem of arithmetic, it follows that p is one of the prime factors of a square. However, using the uniqueness part of the fundamental theorem of arithmetic, we realize that the only prime factors of a square are p1, p2, etc. pn. So, p is one of p1, p2, etc. pn. Now, since a equals p1, p2, etc. pn, p divides a. Example, prove that root 3 is irrational. Root 3 is irrational. Solution. Let us assume to the contrary that root 3 is rational. That is, we can find integers a and b be not equal to 0, such that root 3 equals a by b. Suppose a and b have a common factor other than 1, then we can we can divide by the common factor and assume that a and b are co-prime. So b root 3 equals a. Squaring on both sides and rearranging, we get 3b square equals a square. Therefore, a square is divisible by 3, and by the theorem 1.3, it follows that a is also divisible by 3. Theorem 1.3 is, let p be a prime number if p divides a square, then p divides a, where a is a positive integer. So, we can write a equals 3c for some integer c. Substituting for a, we get 3b square equals 9c square. That is, b square equals 3c square. This means that b square is divisible by 3, and so b is also divisible by 3, using theorem 1.3 with p equals 3. Therefore, a and b have at least 3 as a common factor, but this contradicts that fact that a and b are co-prime. This contradiction has arisen because of our incorrect assumption that root 3 is rational. So, we conclude that root 3 is irrational. Move on to the next question. Prove that 3 plus 2 root 5 is irrational. Prove that 3 plus 2 root 5 is irrational. Solution. Let 3 plus 2 root 5 is rational. Therefore, we can find two co-prime integers a and b such that 3 plus 2 root 5 equals a by b, where b not equals 0. Therefore, a by b minus 3 equals 2 root 5. That implies a minus 3b by b equals 2 root 5, implies a minus 3b divided by 2b equals root 5. A and b are integers. Therefore, a minus 3b divided by 2b equals an integer minus 3 into an integer all divided by 2 into an integer. That implies a minus 3b the whole divided by 2b is a rational number. That implies 1 is rational, root 5 is rational. But this contradicts the fact that root 5 is irrational. Therefore, our supposition is wrong. 3 plus 2 root 5 is an irrational. Next, revisiting rational numbers and their decimal expansion. First one, the decimal expansion of every rational number is either terminating or non-terminating and repeating. Second one, for any rational number p by q having terminating decimal representation, the prime factorization of q is of the form 2 raised to n 5 raised to m, where n and m are non-negative integers. Third one, for any rational number p by q, if the prime factorization of q is of the form 2 raised to n 5 raised to m, where n and m are non-negative integers, then its decimal representation is terminating. Fourth one, for any rational number p by q, if the prime factorization of q is not of the form 2 raised to n 5 raised to m, where m and n are non-negative integers, then its decimal representation is non-terminating and repeating. Our question, without actually performing the long division, state whether the following rational numbers will have a terminating decimal expansion or a non-terminating repeating decimal expansion. First question, 13 divided by 3125. 3125 equals 5 into 5 into 5 into 5 into 5 equals 5 raised to 5. That is equals 2 raised to 0 into 5 raised to 5, which is of the form 2 raised to n 5 raised to m. Therefore, 13 divided by 3125 is a terminating decimal. That is, 13 divided by 3125 will have a terminating decimal expansion. Question 2, 17 by 8. 8 equals 2 into 2 into 2, that equals 2 cube, equals 1 into 2 raised to 3, that is equals 5 raised to 0 into 2 raised to cube, which is of the form 5 raised to m 2 raised to n. Therefore, 17 by 8 will have a terminating decimal expansion. Dear students, today we finished our first chapter, real numbers. If you have any doubts, please drop a mail. Thank you for watching.